I'm doing fine.
Coming to the end of a long week. I tell you what, I've had a lot of tutoring hours the last 4 days.
Really?
Yeah.
Has there been some
Everybody,
late ones too?
everybody's preparing for finals. Well, I've
Oh
been
yeah.
going to 9 o'clock every night. Yeah. All right. I was looking at Chapter 5 today,
All right.
and I think my Chapter 5 is probably the same as yours. I've got 8 sections in my Chapter 5. You just have 6, right?
Um, we have 8 sections, but we're only being tested on the first 6 or 7.
Okay, so 5.6 in mine is quadratic formula and the discriminant.
Let me check what 5.6 is in mine. I think that sounds. I have for 5.6 quadratic equations and complex numbers, but we also did
The discriminant.
the discriminant. Yep.
I'm going to give you
That
an
was included in
equation.
that section.
Tell me what the discriminant is.
All right. I thought the discriminant was under the
It is.
square root symbol.
It's the b squared minus the 4ac. It's not with the radical. It's the part that's under the radical.
Oh, okay.
Okay, so what is b squared?
2x squared?
No, the b is,
Or
this is the b, this is the a, this is the c.
Oh, okay. So the b squared is the negative 3x.
Just the coefficients.
Just the coefficient. Okay, so it would be so negative 3 squared would be 9 minus 4, 2, and then 10.
So the discriminant is 9 minus 80, or minus 71. So that's the discriminant.
Okay.
In other words, when they say, what's the discriminant of a quadratic, they want a number.
Oh, and then on the test they would probably just ask me just to solve it down like that.
Well, the reason the discriminant has its own name is because depending on whether that's positive or negative tells us whether we have real solutions or imaginary solutions. And the one I made up where the discriminant is negative 71, that means at some point we're going to take the square root of negative 71. So
and we're going to get
imaginary answers. So a lot of times it's very useful to know in advance whether you're dealing with a quadratic that produces real solutions or imaginary solutions. And the way you determine that is by analyzing the discriminant. If the discriminant is greater than 0, it's real. 2 reals. If the discriminant is less than 0, 2 imaginaries. If the discriminant is equal to 0, then you have precisely 1 real. Why? Let's look at the quadratic. X equals minus b plus or minus the square root of the discriminant all over 2a. Well, if the discriminant is 0, this whole thing disappears. So the solution would be whatever minus b over 2a is, but it's only one number. It's not a plus or minus, so you don't have 2. You only have 1. So
because that removes the plus or minus. Okay.
Exactly, and that's why the discriminant is so important. Is it gives you so much information about the solution that frequently the first step that you might want to take is to solve the discriminant. Because maybe you have a problem where, gosh, if it's got imaginary solutions, you're not interested. Well, I mean, you can have problems like that. You can have real life problems where if the solution is imaginary, you aren't interested. It's only real solutions that you're interested, and that'll tell you immediately. So that's why it rates its own name in the table of contents.
Yeah, I was wondering why it had why there was a specific like new name for that part and why we learned about
That's
it.
why. Now I see something else under 5.5, finding maximums and minimums.
Is
that something?
What we have to do is we'll have to find like the max or minimum using our graphing calculator.
Okay.
But we never like learned a procedure on how to do that.
Well, I can, in 2 seconds, I can kind of describe it to you.
Okay.
If that's my parabola, in other words, all quadratics graph as parabolas. They're either upside right or they're upside down like that. But they all graph as parabolas. Well, notice that if they're right side up, the minimum is right there always.
Okay.
If they're upside down, then that's a maximum.
Right.
So the vertex is the key.
Oh, just the vertex, isn't it?
It's just the vertex. The y-coordinate of the vertex is the minimum in this case. And the x-coordinate of that vertex would be where the minimum occurs. In other words, this is the y-axis, this is the x-axis. And so if you knew the formula for the vertex, and there actually is a good formula for the vertex, for the x-coordinate of the vertex, guess what? It's minus b over 2a. The first part of the quadratic formula.
Oh yeah, that's the exact same thing.
Yes, it is. And that's one way to help memorize either the quadratic or the vertex. In other words, you've got the quadratic memorized pretty well. So it's going to be a piece of cake for you to memorize the vertex. But
so that's just, it's a part of the quadratic.
It's the first half, what I like to think as the first half of the quadratic. But notice that that gives you just the x-coordinate. In other words, that gives you this value here. Let's say I solve that and I get 3. That does not give me the minimum value of the function. I have to go back into the function and substitute 3 for x to figure out what y is.
Oh, so then you just plug it back in. Okay.
And that gives you either the minimum or the maximum value. So that's conceptually how you do it, but we probably don't want to spend our energy doing that if you don't have to know that.
That's good to know for future, because we'll probably have to do that later on.
You will have to know that for sure. And you will have to find minimums and maximums manually, not just on your calculator. You know how to do it on your calculator, though?
Yep.
Okay.
Do you have the TI-83 or something like that?
I have the TI-84 and the Inspire, but my TI-84 doesn't work anymore. The batteries went bad, and when I replaced them, I couldn't get it to reboot. I think it lost its operating system. And since I have upgraded to the Inspire anyway, I'm not going to replace my TI-84.
Is that one better, the Inspire?
It is quite a bit better, but it's quite a bit different. So it's a big learning curve, and that's why most kids probably tell you they don't like it. You probably have some friends at school that have one, but it's much more powerful.
Gotcha.
It'll do a lot of stuff, and it displays stuff in correct form instead of, you don't have to go 2 to the power of 3. You don't have to do 2 cubed that way. You can actually write it like that on the Inspire.
Oh, so it looks
correct.
Like the same as
Yeah,
if you
looks
were
correct, yeah. So it's better in that way. But either one of them, it's easy to find the minimums and maximums.
Yeah.
So let's see. What else do you need to work? Complex numbers. Let's talk a little bit about complex numbers.
Yeah, complex numbers and operations with complex numbers.
I was just going to do that. First of all, let me write a complex number and another complex number. If I want to add those, just add parts. So what's the solution?
Okay. The solution is going to be the 2 and the 5, so 7 and negative 4.
Negative
4i. Negative 4i.
7, negative 4i is the solution. If I am subtracting negative complex numbers, I'm going to subtract parts. What's that solution?
That is going to be, so in this case, would you distribute the minus in to the right side? Is that what you do?
Well, the way I prefer to think about it is let's do 2 minus 5, and then let's do 3i minus a minus 7i. In other words,
so we end up adding.
I'm just going to subtract parts in the same way that I added parts. So the first thing is 2 minus 5, and the second thing is 3i minus a minus 7i. So it's minus 3, 10i. That's the solution for the subtraction.
Okay.
And that's all you have to do. You don't really need to think about distributing that. You need to think about that's that minus that, and then it's this minus this whole thing. So in a way, I guess you do distribute it. But
that way it's a little simpler to think
I think
about.
so, yeah. And so addition and subtraction is quite easy. Multiplication isn't hard. You just FOIL them. FOIL those for me.
Okay, so then we're going to get, so we're going to multiply the 2 and the 5, so 10 plus, 10 minus 14i plus 15i minus 21i squared.
Okay. Now, the key is I squared is equal to what?
Negative 1.
Good. So whenever we run into an I squared, we're always going to substitute negative 1 for it.
Oh, so I can that'll just turn into
plus 1i minus 21 times negative 1, which becomes plus 21. So it becomes 31 plus I.
Okay, so if there's an I squared in an equation, you can just substitute it for a negative 1.
You always need to. Don't ever leave an I squared without substituting negative 1 for it. And it turns the I squared into a real number. In other words, negative 1 is real. So I can then combine that with the other number.
And that's a lot simpler.
Well, so addition, multiplication, and subtraction are really easy as long as you know I squared equals minus 1. The only thing that's a little difficult is division.
Oh, yeah.
That's because you don't really divide. This is not really a division problem. Looks like it is, but in the same way that if I had this, that's not a division problem either.
No.
That's a rationalize the denominator problem.
So we end up doing the same process as that, right?
Similar process, except instead of multiplying by the square root, we're going to multiply by the conjugate of the denominator, top and bottom.
So we're going to end up multiplying by 5 plus 7i.
The reason I can do that is because that divided by that is the number 1. And you can multiply any fraction by the number 1 without changing its value. So that's what allows me to do that. And by multiplying by the conjugate, I'm going to lose the I from the bottom, which is what I want to do, because you're not allowed to have an imaginary denominator. Just like you're not allowed to have an irrational denominator.
Right.
So we need to not rationalize the denominator, we need to realify it, if there's such a word. But when I multiply this by its conjugate, I get 25 minus 749i squared. Both middle terms cancel one another out. In other words, what I really get, just not to confuse you, is 25 plus 35i minus 35i minus 49i squared. And whenever you multiply by the conjugate, you always get two terms in the middle that cancel one another out. So you can kind of ignore the middle two processes of foiling and just work with the first term and the last term. Now, what's 25 minus 49i squared?
It's going to end up being 25 plus 49.
Okay.
So,
70.
Yeah, 74.
74. So that's our new denominator, a real number. And
which is what we wanted to achieve.
Right. And then we have a numerator that is 2 plus 3i times 5 plus 7i.
So then we're going to get...
we're going to FOIL that.
Yep. So we get...
What do we get?
10 minus 14i plus 15i, so I
think it's 10 plus 14i? Plus...
Oh, yeah.
This is a different problem than the first one, because remember the first one we were multiplying by 5 minus 7i.
Oh, yeah, whoops, I copied down the wrong... I put, for the conjugate, I had, instead of 5 plus 7i, I had 5 minus 7i.
Oh, okay. The conjugate is, the middle sign is the opposite. That's all it means.
Got it.
In other words, the conjugate of, what's the conjugate of I?
Negative I?
Yeah, because I is really 0 plus I. So its conjugate would be 0 minus I, or just minus I.
Awesome. So there, okay, there we go. So we get 10 plus 14i plus 15i plus 21i squared. So then we can condense those. Oh, and then the 21i squared is going to become a negative 21.
So now we get minus 11 plus 29i. So we've taken the imaginary denominator, gotten rid of it. We still have an imaginary numerator, but that's okay. You can't get rid of the I altogether. But we switched it from the denominator to the numerator, and that's all we need to do. And there's our answer. So processes of imaginary numbers are really fairly simple. And there's really only one other thing you need to know. Unfortunately, Casey, I got to leave at 8:30 tonight. Right after I got off the phone with you, somebody took that 8:30 spot.
Oh, that's fine. No worries.
So I'm going to have to go at 8:30.
Yeah.
The only other thing that you really need to know about imaginary numbers is this. What's I to the third equal?
Negative I.
And I to the fourth?
1.
And then all others are multiples. It repeats. I to the fifth is I to the sixth is minus 1, I to the seventh is minus I to the eighth is 1. So what is I to the 500th power equal to?
Oh, my teacher had a way of figuring these out. So I'll like explain her method real fast, and then like maybe it matches up with yours.
Okay.
So what she does is you're going to divide 500 by 4.
Right. Same method I'm going to use.
Same method? Okay, cool.
And deal with the remainder.
Right.
Since the remainder is 0, then that's equal to I. Excuse me, that's equal to 1. In other words, if I took this one and divided that 4 by 4, I would not have any remainder.
Exactly.
So it's the same as I to the 4th. I to the 501 power would be, the remainder is going to be 1, so that's the same as I to the 1st.
Which is equal to the square root of -1.
Right. Right. But the problem you're going to have to do on any test is going to look like that. It's probably, in fact, I've frequently seen 500, but maybe this. As long as you know that if it's divisible by 4, it's equal to I to the 4th, or 1.
So if it's divisible by 4, it's equal to I to the 4th.
Otherwise, it's whatever the remainder is. In other words, in this case, the remainder is 3, so it's I to the 3rd.
Oh, and then if the remainder is 2, it's going to be I to the 2nd.
Right. In other words, if it was I to the 502nd power, that's the same as I to the 2nd.
Got it.
So any power of I can be converted to one of these 4 right here.
Uh-huh.
And then you can either, 2 of those are real numbers. So you can change any I squared or any I to the 4th to a real number.
Okay.
I can't think of anything else with I that you'd need to know other than, let me just ask you a few of these. What is square root of -100?
Okay, so if we're going to do square root of -100, first what you're going to do is you're going to separate it out into the square root of -1 and 100.
Uh-huh.
And then the square root of -1 is I, but then we're going to have to keep reducing the 100.
No, the square root of 100 is 10.
Oh.
So it's just 10i.
10i, yeah.
Okay. Let's take a slightly more difficult one.
Square root of -80. So we're going to go square root of -1, square root of 80, and then from there, can 80 be square rooted in anything?
Actually,
besides like 10?
Yeah, 16 times 5. And 16 is your perfect square number. Now,
so are you always searching for a perfect square when you do this?
I am. That's the way I do it. I've heard teachers use various methods to simplify these radicals. But a good thing to memorize is your perfect square numbers. Oops, I left one out. 16, 25, 36, 49, 64, 81, 100. There's your perfect square numbers. And when you're looking to factor the 80, you're looking for one of these numbers to be a factor. Well, 16 was, so was 4. I could have done 4. But it's longer. In other words, it's extra steps. Notice what happens. I can do 4 and 20. Okay?
Okay.
That's most people wouldn't see the 16, but they would see 4 times 20. So that is, the 4 becomes a 2. So it's 2 times root 20, but the root 20 is root 4 times root 5. So now...
So then that...
Go ahead.
So then that, the root 4 becomes 2, so then you're going to have I 4 root 5.
There you go. So the way to write that
So
is really this way. You
okay.
don't want the I in front. Even if there's a radical sign and there's a danger of this being read like that, and there always is, but
yeah.
nonetheless, the standard format for imaginary numbers is that where the coefficient is in front of the I. So you don't write very often where you would never write it like this. It would always be 2I, not I times 2. It means the same thing, but
yeah.
All right. I think that covers it, Casey.
Yeah, I feel really prepared for this test tomorrow.
I think you should feel that way. I think you are prepared for it. So
awesome.
good luck.
Thank you.
You're welcome. Talk to you next time.
Thanks. Have a good one.
You too. Bye-bye.